Hello guys and welcome to this video brought to you by EDUCALL. So we're going to start with physics, which is advanced level. Now with this we are going to take the first part of it, understanding base units, dimensions and everything concerning it. So basically advanced level physics is divided into main parts where we have the mechanics part, we have waves part, and we have a thermodynamics part. We're going to be treating that in this, so stay tuned for more. So as I said, we'll start with the chapter 1, which are physical equations, homogeneity and dimensional analysis, for you to better understand when we'll go further. So please, for those new on this channel, don't forget to subscribe for more content because it encourages us. I will just hold on for 2 seconds for you to do that. Okay, I believe you must have subscribed. If not still, please do so. Thanks. So, we begin with the first, which are physical quantities. So, what are physical quantities? They are simply quantities which we can touch. That means we see daily, as the name says, physical. And they are divided into two, which are base quantities and derived quantities. Now, why base quantities? Base quantities are the quantities we deal with practically every day, while derived quantities are actually gotten from the base quantities. Now, there are 7 of these base quantities. As I said, we are used to them. That is mass, length, time, electric current, temperature, light intensity, and the amount of a substance. While with derived quantities, they are simply obtained from base quantities, either by multiplying, dividing, and all. So they are like velocity, which is a base derived quantity, which is simply the combination of length and time. Now, getting this, we know velocity is equals to the distance all over time, and this is simply telling us that what the unit is meters per second. We'll get into it when we go further. Now for momentum, which is a combination of mass and velocity, represented as that equals mv, which is called a derived quantity. Now let's get into types of base quantities. There are basically 2 types, which are scalar quantities and vector. As we all know, what are scalars? Scalars are simply quantities having just magnitude but have no direction. Examples are distance, volume, density, speed, mass, energy, power, time, work, pressure, temperature, entropy, charge, gravitational field, strength. Take note of that. Now, what is a vector? A vector is one which has both the magnitude and has a direction. They are displacement, velocity, acceleration, force, momentum, impulse, moment, and gravitational field. Take note, gravitational field. Gravitational field is different from gravitational field strength. We are going to see that if you stick along. Don't forget to subscribe and hit the notification bell for you to have this video when it's out. Okay. Now, expressing the base units and derived units. Now, base units are 7 in number and as follows. We have kilogram for mass and represented as kg, meters for length and represented as m, seconds for time represented as s, amperes for current are represented as A, Kelvin for temperature represented as K, amount of a substance is mole, candela for light intensity. Take note of this unit, for we will be using it throughout this course. Now, derived quantities are obtained by combining, that is combining the base quantities as I said. Now they are velocity, which is simply distance on time, and distance represented as length, given as the unit of length is meters and time has units s. So we are left with meters on seconds, which give us meters per second. As I said, it's a combination either by multiplying or dividing. When we take examples, you see it clearly. Now force given as ma from Newton's second law. Here m is the mass and has units kilograms. A is the acceleration, where acceleration is defined as the rate of change of velocity. Hence we have kilograms representing the mass, meters per second squared representing the acceleration. Now charge is simply as from the equation q equals to it, where I is the unit of current and t is time, represented as unit s. Hence we have as. Magnetic flux, which is given as kilogram per second squared per ampere. In the long run, we're going to see that. Let's not get to, just don't forget to subscribe so that you will have it when it's out. Now let's get into dimensions. Take note, dimensions are different from base quantities. Now dimension is a way of writing down physical quantities with respect to their base units. Hence they are written as such with such brackets, where x there represent the dimension. So for mass, the dimension is written with such braces with m, capital M. Take note. Length or distance is represented as L, capital. Take note of that, please. Time represented as capital T. Electric current, capital I. Temperature, theta. Amount of a substance, N. Good. Take note, never to mix up this with base units. I repeat again, never mix this with base units. So let's get into homogeneity and correctness of a physical equation. This you should really take note, because this is where the topic is centered. Now homogeneity simply brings the idea where all the terms in an equation must be equal, meaning the right hand side of the equation must have the same base unit or dimensions with the left hand side of the equation. Take note, when working with problems, choose one. Either you work with dimensions or you work with base units. Example, let's see if this is the case. Show if the given equation is homogeneous. We have F equals ma, which is the equation for force given by Newton's second law. Here we have force, we have mass, and we have acceleration. So let's deal with the left hand side of the equation, which entails force. From our pre-knowledge, we know that the unit of force is Newton, and Newton is simply kilograms meters per second squared. That is the left hand side of the equation, which has been broken down. Now I'm doing this for further explanation to make you understand detailing. That's why I'm using both dimensions and base units. Now for the right hand side, we have m representing the mass with its unit kilograms, and acceleration. To have acceleration, what did we do? We firstly took this velocity on time, which is simply where the velocity here is simply distance on time, given as meters per second. And now
we'll have meters per second given here. Now we take this meters per second and substitute it back in this our formula, where V is meters per second divided by time, and time is seconds, which gives us meters per second squared. So multiplying the two, that is the kilograms we have, we multiply the kilograms and the meters per second squared. It gives us kilogram meters per second squared, which is still the same newtons we have from the left hand side of the equation. Hence, this equation is homogeneous because the right hand side of the equation is equal to the left hand side of the equation. Feel free to resolve. Now, the correctness of a physical equation. The correctness of a physical equation simply brings us the idea that what the equation must be homogeneous firstly for it to be correct, and not only homogeneous, take note, not only must it be homogeneous but have the correct unitless constant. Take note of that, please. This is very important. It must be homogeneous and contain the correct unitless constant. So, for example, if we take kinetic energy, which is given by this Ke equals to half mv squared, where m is the mass and v is the velocity. If this equation is correct, is energy actually. So here both equations are correct. That means this equation is normally correct because this is the formula for Ke. But now the equation is homogeneous also. Now look at something. If I give you this equation as Ke is equals to 1/3 mv squared. Now, if you only check for homogeneity in these equations, they will be homogeneous, but they will not be correct. They will be homogeneous, but not correct, because they have wrong constants, unitless constants. They have wrong unitless constants. Take note of that. Hence, making the equation wrong. They'll ask the question, is it possible for an equation to be homogeneous and not correct? Yes, because of the presence of wrong unitless constants. Take note. So, as I say, note again. For an equation to be correct, it must be homogeneous. Take note, homogeneous, and have a correct unitless constant. Take note. Hope you have done that. Jot that somewhere. Now, let's get into the examples in this part for you to better understand before we solve a lot of questions. Don't forget to comment. Give your comments so I can ameliorate on the videos and know what your problem is exactly. So now, what are the dimensions of the following? Here we are dealing just with dimensions. Energy, momentum, Planck's constant, density, pressure, and charge. Hang on for the solution. You can try this. Just pause the video and try this before resuming. Well, I begin with momentum. Momentum is simply a product of mass and velocity, given as P equals to mv, where m is the mass and v is the velocity. So, since we're working with dimensions, we're going to have m in these braces representing the mass, lt to the -1 representing the unit, that is meters per second squared, per second, sorry. Now, you leave your answer as such because we are working just with the dimensions. Take note, when you are asked to find dimensions, you leave your answer as such, just like this, nothing more. Don't take it to the base units unless you are asked to do so. Now, energy. Energy is simply the ability to do work, hence has the same dimensions as work. And what is work? Work is simply the force times distance, and we know force is simply what? mass, it's a combination of mass, length, and time, where Lt to the negative 2 simply says it is acceleration, hence multiplying the mass times acceleration and with another distance d, which is L. So if we join these two L's together, we are going to have this ml squared to the ml squared t to the minus 2. That is the dimension for energy. Now, Planck's constant. Planck's constant, we are going to see into that when we get detailed into our course. So stay tuned, comment, let me know your problems as I say once more, so that I'll produce more wonderful videos, so that you will not face problems in your studies. Now, Planck's constant is given as E equals to hf. Don't be scared for the equation now. More are going to be coming when we get into this thing, into the physics you understand. So now, Planck's constant, here we have E given the energy, h is the Planck's constant, and f is the frequency. Now, to make h, which is the Planck's constant, the equation is the subject of the formula. So we have that. Hence, we are to find the dimensions of energy and divide it by the dimensions of frequency. So knowing very well the dimensions of energy, as we earlier did, is ml squared t to the minus 2. And so frequency, we know very well frequency is from period, which is the time for a complete oscillation to be done. Now is given as per second, which is going to be t to the minus 1. So if we divide this, we see that this t to the minus 1 moves up, is going to move up here, and when it moves up here, from our laws of indices and logarithm, we are going to be left with just a minus t to the minus 1, sorry, hence giving us a dimension of that is ml squared t to the minus 1. Hence this is the dimension for Planck's constant. Hence, please jot this down and try it as many times, so it's going to stick in your head. Now, for all these equations, I'm going to drop them in the description below, so that you may have a vivid look at it, so you will not be lost in our subsequent videos, because we'll be solving more and more questions as we go by. So, as I said, we are going to be solving more and more questions. Now, let's target this one, GCE 2005, 2007, which we're going to focus on is dimensional analysis. Now, the question says, explain what is meant by homogeneity of a physical equation. Roman 2 says, show that the equation c squared mu naught epsilon naught is equals to 1 is homogeneous, where mu naught is the permeability of free space and epsilon naught is the permittivity of free space, and c is the speed of light in air. And Roman 3 says we should calculate the value of epsilon naught. Now let's do this together. Don't panic because of these equations or something. As I said, I'm going to drop as many equations in the description below, so you may have a glance of it. In a long run, you'll be a pro in this, trust me. So, solution. Homogeneity is simply demonstrating that additive terms in a physical equation have the same base units or dimensions. That means the additive terms are the same. That's simply what they're asking you to explain there. Now, for Roman 2, here c is given as the speed of light, and speed, as we all know, have dimensions lt to negative 1, which has base units meters per second, but now it is squared, so we square them and we have this. We square them and we have this. So epsilon naught, where are we going to find epsilon naught? Now I know most of you are new into this, you're just coming from ordinary level and you are just surprised about all these things. Now, as I said, I've dropped down those equations. Make sure you read them in the description below. Please read them because we'll be using things here. But this epsilon naught can be gotten from the equation of electrostatics. Here, force, which is given as Q1, Q2 on 4 pi epsilon naught r squared. We see that we can find epsilon naught here, right? So we simply make it the subject of the formula. Making it the subject of the formula, we'll have Q1, Q2, 4 pi f r squared, where Q is the charge, F is the force, and R is the radius. So now, let's find the base unit of epsilon naught. So we know that Q is equals to IT, which is charge, is equals to the current times time. F is equals to MA. So Q is going to have unit AS, where A is ampere and S is seconds. F equals to kilogram meters per second squared, as we earlier did, and the radius is simply represented in meters since it's a length. Now, epsilon naught is simply going to be replacing these base units in the equation. Hence, we have AS1, AS2, where I'll just represent it as AS divided by kilogram meters per second squared times meters squared. Respect their powers too. And now the 4 pi here is just a constant and does not have units. Take note. So we eliminate it. Anywhere you see any constant, here we are checking for what? The base units. They don't have anything to say. Hence, if we evaluate this using laws of logarithm and indices, the A's are going to square up, the S are going to square up, that is the ampere, and the seconds are going to square up. So we already have an A squared, S squared. Now, looking down here, we see we have another S to a negative 2. So negative. So if we carry this up, if we bring this over here, we're going to have a squared. That means a negative is going to leave from a laws of indices and logarithm. This negative is going to leave. So multiplying the S squared from up here, we're going to have S to the 4. S to the 4. Hence, we only have A to the 2, S to the 4. Now, this meter down here and this meter down here are going to give me a meters cube. Now, if we bring it up, it's going to now produce a negative 3. Hence, having this. And this kilogram, same, moves up and produces us a negative 1. Hence, this is the dimension, the base unit, for epsilon naught. So as I said, don't panic. So mu naught can still be obtained from the equation of a force, but this time magnetic force. Now, what is the equation for magnetic force? Magnetic force is given as what? Mu naught I1 I2 L on 2 pi d. We see again another presence of a constant. Take note, it doesn't have units. So we'll make mu naught the subject of the formula. We'll have 2 pi df on I1 I2 on L. Hence, d is distance, which is length, and is going to have units. M, force, kilogram meters per second squared. We have I is current, and current has unit amperes. So there are two of them, so they are going to be squared. And if they move up, they tend to negative 2. And L, which is still a length, is still going to be meters. So we will see that one of these meters goes with this one. We are left just 1 meter, and so these two is they combine to form a square, and they move up here to form a negative 2, and hence the equation kilogram meter per ampere square per second squared. Now we have found that of epsilon naught and mu naught and C. we are good to go to check if the equation is equals to 1 as the question asks us to do. So let's multiply all these base units to see if the equation is going to give us that. So we take c squared, we have this, we take kilogram meters per ampere square per second squared. I will multiply with per kilogram per meter cube, ampere squared, and seconds to the 4. So if we use our laws of indices and logarithm, we see here that what we combine this kilogram goes with this kilogram, this meter squared combines with this one to form a meters cube, where they're going to cancel out with this other meters cube. Here we still have a to the negative 2, which goes with a to the 2, and we see that s to the negative 2 and s again to the negative 2, when we combine them, it gives us s to the negative 4. When we use the laws, this s to the negative 4 brings it out. So we see that all the units actually cancel out, hence bringing them to the powers of 0, 0, 0. Hence we have kilogram to the 0, m to the 0, a to the 0, and s to the 0. Anything to the power 0 in the laws of indices is simply equals to 1. Hence we have proven that that equation is equals to 1. Hence c squared mu naught epsilon naught is equals to 1, as the equation told us to show. Hence the equation is homogeneous since it has justified what we wanted to show. Now they told us to calculate the value of epsilon naught. Now from the equation above, c squared mu naught epsilon naught equals to 1, we are going to make epsilon naught the subject of the formula, where we have 1 on c squared on times mu naught. Hence you need to know the speed of sound in air is given by 3 times 10 to the 8, and mu naught is given as 4 pi times 10 to the negative 7. Calm down, because I'm sure these values are somehow strange to you, but in the way you're going to go further, you're going to see them, so don't panic. So if we put them down, we are going to have 8.84 times 10 to negative 12. That good. So this is the answer, and those are its units as we earlier found, but now we have given it in its form of dimensions. Thank you.